We are very happy to have Michael Chapman, who is a Simons Fellow at NYU. This is the second year.
Third, yeah, starting with third.
He graduated from the Hebrew University, worked with Alex Lubotsky. I think as well. Again, he has done some very exciting work, which we will hear about now.
Thank you, Irit and Avi and everyone for coming and for inviting me. It's a pleasure being here. It is a hard day to give a talk on, as today marks the 1 year since Hamas's brutal attack on Israel, where more than 1,000 Israelis were killed and 200 were kidnapped. 101 are still in Gaza, and I wish they will be free quickly. Let me start the talk. So today's topic is subgroup tests and the Aldous Lyons Conjecture. This is a joint work with Louis Bowen, Alex Lubotsky, and Thomas Vedek. And we refuted the Aldous Lyons Conjecture. This is some conjecture in probability theory that like the object of study is a certain notion of limits of graphs. So only by the fact that it's related to graph, it's related to combinatorics in this seminar, but actually the reason it's natural to talk here is because of our proof method. Our proof method uses complexity theory, specifically the PCP theorem and some soundness results from quantum information theory, and I'll describe all of this when it will be relevant. Great.
Yeah, maybe, and this is one of two talks tomorrow.
Yeah.
So you can tell them what you do tomorrow.
Yeah, okay. So today I'm going to mainly focus on the Aldous Lyons Conjecture itself and its relation to both group theory and to a certain decision problem that you can view as an interactive proof system. I will mainly elaborate it next talk, in the next talk. But I will describe our interactive proof system through the lens of a specific decision problem. And yeah, tomorrow I'll give a more in-depth about our proof. Okay. So what is the plan for today? And I'm giving a chalk talk. I'll have a single video in like 5 minutes or so. So this is still on. So I'll start with an introduction. Quick introduction to cellular automata. Then that probably most of you have heard about, but I'll recall what it is. Then I'll talk about Benjamin-Schramm convergence. Then I'll talk about invariant random subgroups. Afterwards, I'll describe a specific way of generating an invariant random subgroup through finite Schreier graphs. And then I'll talk about characters of groups, specifically characters of the free group. That will be kind of an interlude. It's not extremely important for the talk, but it demonstrates how we got to the proof. And finally, I'll talk about our interactive proof system. So that's the plan for today. And let me start with cellular automata. So a definition, cellular automaton is a local recoloring mechanism of a graph. So to be able to formally define this thing, I first need a graph. And then I need the set of colors. So sigma is some finite set of color. And what is a recoloring mechanism? It's just a function from vertex colorings of the graph to vertex colorings of the graph. Now, I had one extra word there, local. What does it mean for this function to be local? There exists some radius r such that the new color of every vertex depends only on the r ball, the colors of the ball of radius r surrounding this vertex. That's what it means to be a local coloring mechanism.
Is it infinite?
What? Yeah. Actually, the example that I'm going to show, and maybe the most famous example, is Conway's game of life. So, sorry.
These are all the deterministic maps that we have.
What? These are deterministic maps. You can think of it as some dynamical process that you iteratively do, and you have some seed as starting position, and that's usually how they are thought of. So the most famous example is Conway's game of life. And the single video of this talk will just demonstrate it. So we'll see some nice pictures in a moment. But let me just say what is the graph and what are the rules of this specific cellular automata. So the graph is just the infinite two-dimensional grid. I don't know, the group Z squared. The locality is just one. And if this is the grid, we need some more. Okay. So this vertex is adjacent to the 8 vertices surrounding it. So the locality, like the new color of this vertex, will depend only on its own color and the 8 vertices surrounding it.
I equals 2.
Wait, what?
Isn't it I equals 2? If this is the graph.
For me, a ball of radius 1 includes the vertex itself and its immediate neighbors. So these are the immediate neighbors of the specific. The grid is okay. So I think of the squares as the vertices of this graph, not the dots on the Just because I want you to see the colors.
You have diagonal edges.
Yeah, I have diagonal edges. I don't know. It's the ball. I think the neighborhood is defined by the generators who have L infinity norm 1. Like if you think of it, this is the 0, 0 position. And these are all the L infinities, ball of radius 1. Anyway. Okay, so that's just like the neighborhood on which the new color will depend on. There are 2 colors, usually called dead and alive. And I'll say the rules, I won't write the rules, but I'll tell you them. If a vertex was alive, it will stay alive exactly when it has 2 or 3 neighbors that are alive, okay? And a dead cell stays dead unless it has exactly 3 living neighbors. Okay, these are the rules, very simple. But I think the reason these simple rules and this simple setup is interesting is exactly because it generates something that is both very beautiful and very complex. Okay, so let's see a short video. Okay.
I think the projector shut off. Sorry.
Oh, so I need to.
No, I just powered it on. It'll just take a second. Sorry about
You
that.
powered it on from your.
Yeah.
Okay, so I don't need to touch anything.
Yeah, it's warming up.
Oh.
I didn't know.
We've done all the preparations. Okay, so maybe I can say something before we see the video. Okay, maybe I will say something before we see the video because I have time. It will be important in a moment that this set of rules that you will see in a moment, it's not an injective set of rules. What do I mean by that? This recoloring mechanism, this function psi, is just not an injective function. There are 2 starting positions that after one step become the same situation. As an example, you can start with all cells living. And if you heard my rules from beforehand, it means that after one step, they'll all be dead. And you can start from the all dead situation and they will stay dead after one iteration. So it will be important for us that in this example, okay, start seeing something. Let's do one step back.
Can you repeat the rules, please?
Yeah, whenever you have a living cell, it will stay alive exactly when you can already start seeing things go around. So 2 or 3, you stay alive. If you're dead, you will become alive only if you have exactly 3 living neighbors. And as I said, these are very, like, one of the, why is it called life? Exactly because very simple rules generate very complicated behavior. Okay, that's like the motivation. And you can see, I don't know, like there are these 2 generators of these are usually called gliders and they annihilate each other. And there's a lot of things going on. And it's only by repeatedly iterating the recoloring mechanism that I described a moment before.
These pictures you're showing have very specially chosen initial conditions.
Right, exactly. Like
what would
from
happen-
some specific initial conditions, you get very complicated situations. For example, here you get these spaceships that go to the right and stuff like that. And actually this can be thought of as some computational model, and this is a Turing-complete computational model.
What would happen if you had a generic initial condition? Would you still see it?
I don't know how to sample a generic point in the vertex coloring, but I think it is interesting to define some notion of.
Take them independent of probability P.
Okay, I don't know. That's a good question. I actually know nothing about that.
It's actually well understood situation.
But is it complex or is it not complex? That is kind of the question.
It's also, yeah, there is some interesting dependence on the rule.
I see.
Okay, but I'm done with the video, so we can roll this up.
I guess my question is the complexity caused by the very special person in this condition, or is it really generically complex with these?
Yeah, that's a good question. Like, if you say that it's already known, but I don't know. That's for sure. Okay, great. So as I said, this set of condition of starting of rules, of recurring rules, is not injective, but Gottschalk was interested. Gottschalk, I think from 76, was interested in the following question: injective cellular automata also surjective. So if you cannot get to the same color situation from two different situations, doesn't mean automatically that you can get to anyone. Okay, that's the question. And there is an answer to this question. Surprisingly, the answer is no in this generality. Okay, so in this generality, the answer is no. There are known transitive graphs for which this is not true for. But for the Cayley graph situation, this is still wide open. For Cayley graphs, this is wide open.
Finite or infinite?
Okay, so for finite graphs, this is obviously true. And that's my, actually, that was my next remark. Thank you, Peter. So at least for one class of graphs, this is clearly true, just because this set is finite. Injectivity implies surjectivity for functions from a set to itself, right? And the amazing observation of Gromov and Weiss, so first Gromov from 1999 and then Weiss from 2000, is that when the graph G is the Benjamin-Schramm limit of finite graphs, Gottschalk holds. Then Gottschalk holds.
Gottschalk question.
Yeah, Gottschalk is not the person, this question of Gottschalk.
Not a question. Are they injective? You mean the answer is yes?
Yes, okay, then yes to Gottschalk. Yes, thank you. Yes to Gottschalk. Thank you very much. And that's exactly the nice observation, right? Like there is a class of objects for which the answer is clear, and we define some limiting operation, and somehow the property goes to the limit. And that's the nice result here. And these, so I didn't define Benjamin-Schramm. If you recall, I'm going to define what Benjamin-Schramm limits are in a moment, so don't worry, but I will just give you some naming to these things. Usually a Benjamin-Schramm limit of finite graphs.
Is B a Benjamin-Schramm?
Yeah, if G is that G is a Benjamin-Schramm limit of finite graphs, these are usually called sophic networks. And if the graph is a Cayley graph, the group is usually called a sophic group. This is just a name people sometimes hear, so I wanted to just clear it out that that's exactly saying that for sophic groups, Gottschalk conjecture is true. Okay. Great.
The sophic network, the system.
I said a Benjamin-Schramm limit of finite graphs is called a sophic network. Yeah. And I didn't define it, what is it, but just that's a naming of something, and the word sophic is like well known, so I wanted to clear this, that let's actually ask something about this notion of soficity, or shows that soficity is interesting, and maybe this initiated the fact that soficity is interesting. Okay, and since then, sophic groups are well studied, and many things are asked and also known about them.
So now you call it conjecture. So the belief is that for Kelly graph, there's
No, for Kelly graphs, in general, it's not known to be true. Even if there is a non-sophic group, it's not clear that a non-sophic group will be a counterexample to this thing. That's widely open. I think people believe that once we have a non-sophic group, maybe we will start understanding why this potentially can be wrong in this generality. Or someone else will show that it's always right? But still, like, we just don't have enough tools to even construct so there are no non-sophic groups. Like, we don't know how to build them, so we don't know how to somehow tinker with this question until we have non-sophic groups. Okay, so it's kind of, we're stuck about this, unless someone will come and show that it's like unrelated to soficity somehow. You can prove it without this assumption.
May I make a small remark? It's not that we don't know how to build non-sophic groups. There are many candidates that are very likely to be non-sophic. We don't know how to prove that.
Yeah, that's correct. Okay, yeah, that's true. But then I think, okay, if you can refute Gottschalk conjecture for a specific group, it will show that it's non-sophic in particular. So you even need to know more than non-sophicity. That can be a tool for proving that something is non-sophic. There are candidates, so maybe there are good candidates to refute this conjecture. I don't know.
Can you give an example of a candidate, non-sophic group?
I don't want to, but there are like very easy, very straightforward, like 4 generators, 4 relation groups that people believe are non-sophic. Yeah, Higman's group, right? Like, that's the name.
Human group, any simple non-amenable group, so there are plenty of very different construction, right? So.
And you believe all of them are non-sophic? Maybe, yeah. That's.
Ask it the conjecture. By the way, why do you say Aldous Lyons conjecture? Did they formulate it as a conjecture? Because
Okay, yeah, I'll get to it. Anyway, let me just define what a Benjamin-Schramm limit is. Okay, so after we have this beginning, so now we know that Benjamin-Schramm limits of finite graphs are interesting. Limits. So this is the topic, and to that end, I need to define several objects. So a rooted graph is just a pair of a graph and a specific vertex in it. These are in topology usually called marked spaces. Okay, so it's just an instance of a marked space. In this case of a graph, we call it a rooted graph. And let's just denote by curly G with a dot upstairs and a D downstairs, the collection of all rooted graphs with that are deregular. Okay, that's just a set. And this is a nice metric space. Okay, how do you see that this is a metric space? You just define that 2 graphs are close, and G prime, V prime are to the minus R close, which means their distance is at most 2 to the minus R. If the ball of radius R in this graph surrounding G, in the graph G surrounding the root, is isomorphic to the same ball in the other graph. So we have some notion of distance, and actually this makes it a compact metric space. So it's a very nice space. And this is also a nice function. Okay, so I think of it as the restriction to the R ball. And note that there are only finitely many radius R balls in the deregular graphs. Okay, bounded amount of vertices, bounded amount of degree. There are only finitely many of them. That will be important in a moment. But Benjamin-Schramm limits talk about actually distributions over this object. So what is a random rooted graph? So that's just some probability distribution, Borel probability distribution over the irregular rooted graphs. And I think for me, when I hear Borel probability distribution, usually it frightens me. So I want to just paint a picture. You should think of it as a black box with a button upstairs that spits out. When you touch the button, it spits out a pair consisting of a graph and a specific vertex.
These are all fine.
No,
No, not necessarily.
the option, you can spit out anything you want.
Okay.
That's actually important. Distributions also over the infinite ones. Great, there's also a metric here induced by the metric there called the weak star, like the, not metric, but the weak star topology. Okay, and so there is a limiting process here as well.
When you say a graph, an infinite graph, you still need a countable in that set.
Yes, all graphs here are connected. I didn't say that. So I think just because my metric doesn't distinguish between disconnected components, right? Like it only sees the component you're in. So these are just connected graphs.
But you could have a graph of an uncountable number of vertices, because then you'll lose separability and you'll have no integral.
No. It's degree D. It's countable just by degree. If it's connected and degree D, it's countable. Yeah, that's the object I care
I
about.
see, I see.
Yeah.
No.
Yeah, degree D and connected
Not the
and
number of
countable.
neighbors, yes, okay.
Yes. Everything is countable. At least this set contains only countable graphs.
This is weird stuff, but it's not set theory.
Moment. Yeah, we'll drink some water. That's that. Great. Now you can push forward measures along this function, along the polar radius R function. So what do I mean by that? You can, if this is mu, you can build a bigger thing, a bigger black box, which we denote BR star of mu. Okay, it's the push forward of the measure. It will output to you a ball of radius R, a random ball of radius R. How does it do it? It first touches this thing, generates to you a random rooted graph, and then it just evaluates the ball of radius R function on this graph, and it gives you the R of GV. Okay, so that's a random, now finite graph out of a finite collection of possible graphs, right? That's important for us. Right. Here. Now we say that a collection mu n Benjamin-Schramm converges to mu. Even only if that's actually a definition, for any radius, the push forward of the measures converges to the push forward of the measures of the target measure. And know that these are infinitely many conditions, right? But these are conditions on finite probability spaces. So this is just a vector with finitely many inputs between 0 and 1 that adds up to 1, because there are only finitely many balls of radius R. So this is a finite dimensional vector. We want it to converge to a finite dimensional vector. We understand very well the right-hand side, and it defines to us the left-hand side. Great. So this is Benjamin-Schramm convergence. And if I'm given, so what I wrote before, it's not here anymore, okay? But I wrote that if something is the Benjamin-Schramm limit of finite graphs, then blah. But we see that Benjamin-Schramm convergence talks about distributions over graphs, not a single graph. So first of all, whenever I talk about a finite graph, I talk about a specific distribution. So given a finite graph, here's finite. I take the distribution where the graph itself is fixed, and here the uniform vertex. So whenever I say that something is the Benjamin-Schramm limit of finite graphs, I mean, first of all, you take this specific distribution of vertices over this graph, and then you ask, okay, is this converging to something? And then you have a limiting object. I'm claiming that this limiting object is a fixed graph if its left coordinate is fixed, right? It's some distribution. I want the left coordinate to always be the same graph, but with some random root inside this graph. So this should clarify this kind of argument. Yes, I wrote here that the Benjamin-Schramm limit of finite graphs. I didn't write the Benjamin-Schramm limit of some distribution of rooted finite graphs. So the point is that whenever you have a finite graph, it defines a specific random rooted graph, okay, which is just choose a uniform vertex. And whenever I say that something is the Benjamin-Schramm limit of finite graphs, I mean with this specific distribution over the vertices.
Like a distribution of some
uniform vertex in some fixed.
Finite graph. Yeah, that's the point. When I talk about Benjamin-Schramm limits of finite graphs.
The limit object will always be infinite, or not always.
No, if you fix the finite graph or all the sequence, it will be the finite graph. Yeah, it can be approximate. Like finite graphs can actually, I think, Noga showed that any finite graph is epsilon approximated by some fixed sized graph that whose size only depends on epsilon, but it's not like it's not effective. Like you don't know how to say how big is this graph. So there are questions about approximating finite graphs by other finite graphs, things like that. But in our case, the interesting case would be to approximate an infinite thing.
I really like this.
This question, or
What Noga showed, but to do it in a more convincing way.
yeah, so you get some computable function out of it. That would be amazing. Yeah. But that's not today's topic, unfortunately. Okay, great. So,
I don't know.
Yes. Prove that any always approximate infinite. How do you approximate?
okay, so let's see some examples because you asked good questions. So for example, we saw the infinite two-dimensional grid. It's not hard to show that if you take just the n by n grids, then they Benjamin-Schramm converge to the infinite one.
Because the infinite object is transitive, then you don't need to define it.
Yeah, that's true. Like because I care only about isomorphism classes, whenever I have an infinite transitive graph, it like I just fix one vertex and always give you this finite vertex, this fixed vertex.
And what would be the distribution on the words?
Here, that's exactly what the one just said. It doesn't matter. I care only about isomorphism classes, so you just fix a specific vertex in the transitive graph, and then it gives you like the output. Okay, great. So this is like the amenability of this two-dimensional grid, and actually the amenability using radius r balls in this graph. And a slightly, okay, so it's easy to show that this doesn't work when you try to approximate the d-regular tree. So if you try to take just balls of radius r in the d-regular tree, there are too many leaves. So with high probability, you will fall on a leaf, and the ball around the leaf doesn't look like the ball inside the d-regular tree. And the way you overcome this is just by taking graphs that have larger and larger girth. Okay, so you just take a sequence of graphs. Yeah. Of the regular, thank you. Graphs with girth tending to infinity. So any sequence of this kind, and we know of examples, tends to the d-regular tree. Maybe I'll keep that upstairs.
Of course, you don't need to get. As long as there aren't many short cycles, it'll be the same.
Right, exactly. So you fix, because of the definition, you first fix the R, and then they only check things. So the girth tends to infinity. At some point, you will see only like the ball in the tree.
Like it's not even like probabilistic statement. That's actually the same distribution.
Yeah, exactly. It will be a fixed graph, which is exactly the same graph. Yeah, yeah, right. It's not approximate. Yeah, that's actually a good remark. Like this is comes from residually finiteness, and whenever you have residually finiteness, you have this property. It's not even in probability. You just at some point in the sequence, for every out, from some point in the sequence, you get the correct distribution from now on. Yeah, that's a good remark. Okay, great. So, yes. What did I want to do now? Let me go to my notes. Sorry that I'm using them a lot. Okay, so some results. Okay, so it's called Benjamin-Schramm limits. Benjamin-Schramm studied it. So let me give you a theorem of Benjamin-Schramm. From 2001. So Benjamin-Schramm limits of planar finite graphs are recurrent. So planar, recurrent. A planar graph is just a graph, finite graph that I can draw in the plane without intersecting edges. So this is a well-known notion. Recurrent is somewhat less known, but is still quite a known thing. If you do the simple random walk on the graph with probability 1, you will come back to your starting position. So it's almost an exercise, but quite a well-known thing that in the 2-dimensional grid, you are recurrent. With probability 1, you'll come back to your starting position. But in the 3-dimensional grid, this is not true. Okay, with probability strictly less than 1, you'll come back to your starting position. And there's a joke about it. Like, the drunk man will arrive home at some point, but the drunk bird may not. So this is a nice thing. And this shows you again that like the idea of Benjamin-Schramm convergence, right? Like somehow being approximated by planar graphs tells you something about like you behave like the plane in the sense of the simple random walk, in this specific sense of the simple random walk. So that's nice. That's under the philosophy of approximating things. Another theorem.
You didn't say the graph would be planar.
That's true. I'm not sure. Maybe it's clear for someone in the audience. I don't know. Yeah. Okay, so also infinite graphs can be planar, and I'm not sure. Okay, so another theorem now by Aldous and Lyons. They show that Benjamin-Schramm limits of finite graphs. So I gave it a name already, but so a Sophic network. Is unimodular. Now, I kind of don't want to define unimodularity. It's some property of a random rooted graph, but let me give you some taste of unimodularity. It's some kind of being a stationary distribution. Okay, so what is a stationary distribution? Is some distribution over the vertices of a graph such that you apply the simple random walks once, you stay with the same distribution. So it's similar here. You sample a graph, you do one walk in the simple random walk, you get to a new vertex, you choose this as the new root of the graph. Is this distribution invariant under this procedure? Okay, so these are unimodular networks. And clearly for finite graphs with the uniform distribution on them, this is true. Whenever you have a connected graph, finite graph, the irregular, the only distribution that will satisfy it is the uniform distribution. So it's natural to choose the uniform distribution on finite graphs. They also motivated here this notion, and they show that this is true. And the headline of today's talk was the Aldous Lyons Conjecture. After proving this, they just asked, maybe I'll write it here.
You mean up to isomorphism? Because these are infinite graphs, so.
Yeah, everything is like isomorphism classes. Everything tends to the
So if
isomorphism.
I pick a random initial vertex according to the measure, I
Yeah.
get that the random walk is what I get isomorphic to the.
Yeah, exactly.
That's the.
So for in a transitive graph, you'll just stay in the same place. Yeah, and there is like a graphing or something that you can define here, and this is like better defined over the graphing instead of in this context, but really I don't want to. Wait. This is not important for us, although it's extremely interesting. And their conjecture, it's just from the same paper, is the reverse true? So
That's a question.
that's okay. So in the original paper, it was a question. But it's common, even like Aldous in his open problem section calls it the conjecture, although it was posted as a question. But I'll stick to the name conjecture. At some point, we changed it throughout the paper to problem. But it is so uncommon to see it called the Aldous Lyons problem. So but it's a question. Are unimodular the problem? Are unimodular networks always solved? Yes.
So when you define the Benjamin-Schramm limit, it's a limit to a distribution.
Right.
So how do we know we get an infinite graph?
How do we know that we get an infinite graph?
It's an infinite graph and not an infinite sequence of numbers.
I think that whenever you have a finite graph, you will be, at some point you will see the whole graph, it's the connected thing, and then you will be, your measure will be concentrated on a specific, you will see the whole graph at some point and you will concentrate it on it, right? So you can see that you're not approaching a finite graph by just seeing that you're not concentrated on the part of the distribution that is supported only on finite graphs, right? Like there is, you can see somehow that you're
When you
not.
say Benjamin-Schramm limit of a sequence of finite graphs, and you say this object is an infinite graph,
With a measure.
Yeah, it's with a measure, and when I say, okay, so when I say it approaches a specific graph, I mean a graph with a fixed graph with some distribution on its vertices. That's what I mean when I say it approximates a specific graph. Usually it approximates some distribution over graphs, comma, vertices. When I say it approaches a specific graph, I mean a fixed graph, comma, a distribution over the vertices.
okay, so when I read this conjecture, I should think you already have a sequence that you know approaches.
No, this problem or?
What is a unimodular net?
Yeah, so a random rooted graph satisfies unimodularity if it's invariant under the following process.
A finite object?
No, that's a distribution over the set, this peculiar set G dot D. Okay, that's a distribution over this.
Remind me what that is?
The irregular graphs with, these are pairs of some deregular graph,
Infinite?
potentially infinite. There are like all the deregular infinite connected graphs are here, comma, some specific vertex in this specific graph.
Okay.
So when I say you approach a specific infinite graph, usually I mean this is fixed, but this is still some distribution over the vertices. But in general, this object, the unimodular network, is a random rooted graph, so a distribution over rooted graphs that satisfy the property that if you first sample a graph and a root, and then you move uniformly to one of the neighbors of this vertex, you stay with the same distribution. That's the important thing. Clearly, you're not in the same vertex, but you're in the same distribution over isomorphism classes of rooted graphs.
And the conjecture was initially on regular graphs, or?
No. It's not only for regular.
When you refute it, you refute it anyway.
We refute it in a more restrictive case of Schreier graphs, which gives you. So here I'm not using any labels on the edges, but it's easy to show that whenever you have finitely many labels, you can delabel the graph using some decoration tricks. So this refutes like the most general case of this. That's like the very restrictive case, like the deregular without any labels, it refutes that.
So to refute the conjecture, you need to describe a distribution of unimodular.
Yeah, a unimodular distribution of rooted graphs, yeah.
And so that there's no sequence of finite graphs
that is the limit of, yeah, exactly. And we will do it using complexity theory. Like we will show that if this was true, some decision problem is decidable, but this decision problem is undecidable. That would be the method. Yes.
But decidable, undecidable, I mean, in the work of Vidic code, complexity was used in some way, but in the end, it was more the halting problem that was the.
We will see the halting problem will be here as well, yeah. But I'll get it, yeah.
Just to clarify one more time, if I have the Benjamin-Schramm limit of a sequence of finite graphs, the limit can be a distribution over infinite graphs.
Yes, it doesn't have to be a fixed infinite graph, it can be a distribution over infinite graphs. We will see. Like I will give you examples.
That's why the definition's a good one, by the way.
Yeah, exactly, right. Yeah, it's a good definition exactly because sometimes it's a distribution. Otherwise, if the limiting object was always a fixed graph, it would be like.
That's the only ones I understand, yeah. So that's why it's
I'm
important.
so confused about the order of, I mean, so you insisted that you want before the limit, the things you take the limit of, the graph to be deterministic and only the vertex to be.
Right, that's true. But the limiting object can behave differently. It can be like some distribution.
Of course, but the conjecture here is about general distributions over deregular graphs with random roots.
Right.
So
you ask why did they ask this question? It seems like.
But for example, if you now were to weaken the assumption, if you say are these Benjamin-Schramm limits of
that's always
random graphs, that's always true.
Why random graph? Not random, but any distribution over graphs, clearly, you just take the arbor.
The Benjamin-Schramm limit of a random deregular graph is just a deregular tree.
No, you meant.
No.
No.
I'll say what, okay.
That you have G with the.
Wait. That, like, Ramon's observation is extremely important. Let's note the following. You can always take a unimodular network and take its push forward along the radius R thing, you will get some distribution over R balls, and it's the correct distribution in this object, right?
So as R goes to infinity.
So yeah, exactly. So this sequence of distributions over rooted graphs converges to this thing always. So this is a triviality.
With the root being deterministic.
Like whenever you choose this, it gives you. But this is a distribution over graphs. So
Right.
the middle of the ball is the fixed vertex. You always take this one. So that's like a bad question. Taking any distribution over vertices in finite graphs, that's a bad question. The right question is if you force the distribution to be unimodular on the finite graphs, being the stationary distribution, now it approaches some unimodular network, are all unimodular networks in this limiting set. Okay? And like it's a closure of some set. I'm asking, did I cover all the unimodular networks?
There's still an intermediate question, which is what if I'm allowed to choose a random graph G, but I insist on taking a uniform vertex in a random graph G?
I really like, these are great questions. I just don't know.
Okay, so this is not clear. That's what
Maybe, okay, so Peter just said at least for random graphs, it's known to approach the tree, right? That's part of like the kind of thing you showed. Yeah, but maybe
I'm talking about the question, the conjecture you asked, right? I mean, you could allow G to be random, but still pick a uniform, because the unimodular.
That doesn't help you. That doesn't help you. You will show that there are things that are far from any, like what we'll get today is that there are things that are far from disclosure. These are convex sets. Like you can look at all sophic networks. Maybe I'll erase this thing. So sophic networks is some convex set in some infinite dimensional vector space. There is a larger, and now this is a strictly larger set of unimodular networks. And actually the way we prove, what we prove is that we construct them functional such that it gets the value 1 in this set, but in this set it gets only value 1/2 or at most 1/2, which exactly means that this is far away from these. So even if you do what you just said, you take convex combination of these things, you're still not approaching this limiting object.
So just to summarize, because you kept emphasizing that the graphs G have to be deterministic, but that's completely irrelevant. It's really the uniform vertex that's.
Right. I'm only allowed to use these. You can take convex combination of these, but not.
We don't care that G is deterministic. We just need to take the uniform vertex in the graph.
That's true. But just because this set, you get the same thing. That's the yeah.
So since you mentioned decision problems, there's no counting argument, I'm assuming, that would separate them.
No. There's no counting.
That was my question, but you get into it.
Yeah, okay. Great. I'm moving very slowly, sorry.
When Vidic gave his talk here, Avi complained that he didn't say enough word complexity enough.
I will say a lot of things about complexity, but only here, so let me move on. So what is an invariant random subgroup? If we know what the conjecture is. So this is very group theoretical, so I'm sorry for those that are less used to like the group theory definitions. Yeah, but let me dive into it. So you have a group gamma, and you have just the collection of subgroups of gamma. This is just a subset of the collection of all subsets of gamma. That's just an object, and this object is also nice. Like it, this object is nice. It has the Tikhonov topology on it, the product topology. This gets the same product topology, so you can again talk about probability distributions over subgroups. And again, I want you to think of it as a black box that I push and I get just some subgroup of this specific group gamma. Now gamma acts naturally on its subgroups. So this is just by conjugation. So if you have H, the way G acts on it, such GH, G inverse. And again, you can just take the push forward into that like space and you get some action on probability distributions. Okay, so the group gamma acts on its probability distributions by the same picture as before. Maybe I will show this picture again. So now I have a black box phi. It spits out a subgroup H, and it lives in a bigger black box. It's called G dot This is pi, G dot pi, and this just conjugates the subgroup. So this is a new probability distribution, and this means that the group acts on this thing. And an invariant random subgroup is just a fixed point of this action. Here. So an IRS is a fixed point of the conjugation action on the probability distributions over the subgroups of.
So you fix the probability distribution or we consider all probability?
A probability distributions over subgroups is called an IRS. If for every G that you take here,
You get back
the
to
new
that.
black box is the same as the old black box. Yeah? Great. Examples. So the simplest example is just a normal subgroup. And what do I mean by a normal subgroup? Again, this is a fixed object, the Dirac measure of this normal subgroup. So the box that always outputs the same normal subgroup is conjugation invariant, just by the definition of a normal subgroup, it's conjugation invariant. So normal subgroups, Dirac measures over normal subgroups are an example of an invariant random subgroup. A slight generalization of this is any, for any, maybe, subgroup H with finitely many conjugates, calculate the uniform distribution. Take uniform distribution over conjugates. So that's just the generalization of this idea, right? If you have finitely many, okay, just take the uniform, conjugates will somehow permute them, but that's all they will do. Great. A third example, which is the one that is most important for us. If gamma acts on a finite set, so essentially I sent every element of gamma to some permutation on this finite set, right? It's a homomorphism for gamma to the permutations. You can ask what is the stabilizer of a vertex? The stabilizer of the vertex and on a triangle inside omega is just all the elements G in gamma, such that G acts on the triangle and it is still the triangle. And now this is a subgroup of the group gamma, and the way you sample, like you're seeking a random subgroup, so you sample a uniform element in omega. So I use the uniform measure on the finite set, but then the subgroup that I output is the stabilizer of this specific vertex in omega. Okay, great. So we got three ways, and you can check that this is always a convex combination of this thing. Okay, it's actually a convex combination of a specific kind of these H's, those that are of finite index. But that's a very, like, I don't know, operational way of generating an invariant random subgroup. Okay, great. We have. And let's just give a name for those that were generated in this way. These are called finitely describable IRSs. So you have the set. You have the set of finitely describable IRSs of gamma, and you have the set of all IRSs. And you can just ask, okay, is the closure of this set everything? Okay, so question is IRS finitely describe gamma, closure is everything. Is the IRSS of gamma.
What should we be thinking of as gamma as a finitely splintered group? Or what's
So up until now, I didn't say anything of on gamma, right? It was very, very general. We see that at least in like flavor, it's similar to the previous question. We had two convex sets, and this is convex set in some appropriate space. And we again ask whether the closure of one is everything, okay? Like whether you can approximate everything using the smaller set. But this we know the answer. The answer is no, sometimes, and yes, sometimes, depend exactly on the group. Okay, so first answer depends on gamma. Depends on gamma. So we know of amenable groups that satisfy this, that the answer is yes, amenable groups that has a no as an answer, and we have more general groups that we don't know of at all. And Aldous and Lyons asked, Aldous Lyons, same paper. What about the free group? The case where gamma is just the free group. So this is the group without any relations generated by some finite set S. Okay, so all words in S and its formal inverses, where the only cancellation is if you see an element and immediately after its inverse. Great, and now you should ask, okay, how is this problem? Okay, I said it's the same paper, it's actually the same problem. This is just a special case of the previous problem. Okay, and that's what I want to show you now. Any questions about this? That seems very good theoretic, like I could have started with this. Actually, that's what I did in the probability seminar in Berkeley last week. I started with this question.
But this answered much earlier, no?
What?
But this was answered much earlier, no?
Why? I'm claiming that this is what we show. Like we show that the answer is no for the free group, and it was unknown up until now. That's a special case of the Aldous Lyons conjecture. This setup is just a special case of the Aldous Lyons conjecture. It was known for other groups. So when I said depends on gamma, there were groups for which we knew the answer.
So what Bowen showed is all the IRSs of Bowen in the free group.
Yeah, they are sophic by definition. These are, he only uses, like for his entropy arguments, he only uses those that are like limits of Benjamin-Schramm, like Benjamin-Schramm limits of finite graph, finite Schreier graphs. Other questions, remarks?
For which groups it was known, not all, you mentioned some groups, but.
Yeah, there are amenable groups for which this is known to be false. Like this is not, I don't remember, like there are 4x4 matrices. You somehow choose like elements in Z of 1 over P and things like that, somehow smartly.
Matrices, you mean solvable groups?
Yeah, some upper triangular matrices. You choose wisely like the coefficients along this matrix, and somehow this doesn't satisfy it. Yeah, Becker and Lubotsky and Andreas Tom showed that if this is true for a specific amenable group, then this group is what's called stable. So this is somehow related to stability theory in groups, and there are examples for which this is known to be not true. So the closure of this set is not everything. But for the free group, it was open, and it turns out to be just a special case of Aldous Lyons. Let's show that. Unfortunately, I'm really almost out of time, but
You can take 10 more minutes.
okay. Yeah, I don't want the audience to suffer. So, how are these two problems related? Maybe let's discuss that. I believe all of us know that whenever gamma acts on a space, and this doesn't need to be a finite, let's assume it's countable because that's will be our setup anyways. But whenever this is some set, you can draw a graph. Okay, how do you draw a graph out of it? This is the Schreier graph. So that's actually what Ramon did, like, was it a week ago, right? Like 6 days ago, Ramon showed you that if you want to sample a random graph, you can choose a couple of permutations. And this couple of permutations generates to you a labeled oriented graph. He forgot about the orientation and labeling, but I want to remember them. Okay, that will be the difference. So how did he do it? Whenever we had two vertices, triangle and square, in the set omega and some element S. So this is just an element of some generating set. So this is a finitely generated set group gamma. And you have some generator in this generating set S. Then you draw, you act with this S on triangle and you get square. You draw an edge from square to triangle labeled by S. So that's almost what Ramon did. He used the other orientation, but we use this orientation because we read words from left to right, but we act with functions from right to left. That's why this is the weird direction that I choose. Okay, but you agree with me that whenever you have an action of gamma on a set, you automatically get a graph that represents this action.
We're just describing the notion of a Schreier graph.
Yeah,
Oh,
exactly.
okay, yeah.
That's I'm describing the notion of a Schreier graph. But usually when you say Schreier graph, people think of a coarse Schreier graph. This is an action Schreier action graph, and that was also like my headline for this topic. So I am talking about Schreier graphs. Let me take this upstairs. Great. And once you have this thing, you see that always gamma acts on the cosets of some subgroup, right? Like G dot the coset HH is just GHH. Gamma acts on its cosets, then you get the coset Schreier graph, and that means that a random subgroup always can give you, by looking at its Schreier graph, a random Schreier graph. And this is a rooted graph because you can always look at the root being the identity. So you can always translate the random subgroup to a random Schreier graph. And this shows you that at least there is a potential of relating the two problems. And Albert, Glasner, and Virag in 2014 exactly show that if you start from an IRS, what you will get is a unimodular network.
Aha, no, you were using that. That's lovely.
Hmm?
Oh, that's a beautiful paper.
Yeah, that's true. And if you start from the closure of the finitely describable IRSs, then you get a Benjamin-Schramm limit, so a sophic network. So this is genuinely a special case in the case of the free group. So why I'm saying that this is a special case, exactly because this is the most general sophic network on Schreier graphs only when the group you start with is the free group. Otherwise, you see always the relations in this group, right? And in the general sophic network, you shouldn't see any specific kind of walk always being closed. Okay, so the correct analog is the case where this is the free group. Here. Okay, so maybe let me just finish with characters. So a character is some other object which is very similar to invariant random subgroups that I want to define, just because the way it was resolved, like the questions about characters was resolved using complexity theory, and that's the thing I want to head to. So a character is just a function from your group gamma to the complex numbers that satisfies three things. The identity is sent to 1. The function is conjugation invariant. And for any tuple of elements in the group, finite tuple, you can generate a specific matrix. It's the value of Gi inverse Gj for any I and j between 1 and n. So it has ones on the diagonal, and in other places it has some, finish. It has some complex value in the other things, and this will be a character only if this matrix is positive semi-definite. definite.
I mean, this is very close to some abstract definition of a unitary dual.
Okay, exactly. Okay, so that's important what you said, but I don't want to actually define this. But the first example that you should think of is whenever you have a finite unitary representation of your group, whenever you have like.
At least for every G1.
Yeah, for every G1 to GL in gamma, I want this matrix to be some positive semi-definite. So the first example you should think of is a unitary representation. You send your group to UN, this is a homomorphism, and you just take the normalized trace. 1 over trace composed with rho, gives you some character. And these are called the finite dimensional characters. Another example, which is nice, if you take an IRS, okay, you can always ask for any element in gamma, you can ask what is the probability you sample a subgroup according to this IRS, right? And you just ask what is the probability that G is in this subgroup. So the identity is for sure in the subgroup, so the answer for the identity will be 1. It satisfies this first condition. And it's not that hard to show that, okay, conjugation invariant is exactly, we force conjugation invariant in the way we chose the subgroups, right? And the third condition is nice because it's any probability over subgroup satisfy this third condition without any conjugation invariant. That's nice, and it turns out that you can translate any IRS into a character. And that's another example. And I'll draw you the following picture one last time. You have the finite dimensional characters. You have all characters. And you can ask, is the closure of this thing everything? The answer depends on gamma, but you can ask it for the free group, and that's called Cohn's embedding problem. Okay, so Cohn's embedding problem, ask, is this true? When true meaning this is the closure of this, when gamma is the free group. And quite famously by now, I'll draw you just one table and I'll finish my talk. So what did we see? We saw the Aldous Lyons conjecture. We now saw Cohn's embedding problem. Here there is some complexity class called MIP star. And a series of papers, 2 series of papers. One, I want to say 2 theorems. One is due to Navascus, Pironio, and Assin, to Jung et al. Fritz, Ozawa. So many people show that if Cohn's embedding problem had a positive solution, namely for the free group, it was true that the finite dimensional characters are everything, then MIP star is decidable. And then G, Natarajan, Vidic, Wright, and UN showed in 2019 that MIP star contains the halting plan. Great. So now we have a picture. We see that there is a complexity class here. There is a conjecture in pure math here. A positive solution to this implies that this is decidable and this is undecidable. So our proof method is to fill up this bracket. Namely, we're going to define a complexity class. It can be seen as an interactive proof system such that the Aldous Lyons conjecture being true would imply that it's decidable, and we show that it's undecidable. That's what I'm going to talk about tomorrow. Okay.
So, can we ask a question? Thanks. The kind of undecidability, which is the sort of thing that makes everything work, is not complexity theory. So where does the complexity theory?
You just define this as a complexity class. In the usual sense, there is some algorithm that needs to run in efficient time. Yeah, there is an algorithm that needs to
need efficient.
The way you define this complexity class, there is some algorithm that needs to run in efficient time. And actually, there's now, there will come a paper by Andrew Marks, Henry Wen, and like another postdoc that I don't remember his name, I'm sorry for that, that actually showed that this is a very general thing. Whenever you have an undecidability result, you must have a complexity class defined using efficient things that have this compression theorem on it. So in some sense, that's the most general thing you can show. Like whenever you have undecidability, you actually have the structure. That's interesting. So that it will come up soon, their paper. Yes.
Can you comment on, so you have, from every IRS, you can define a character like this?
Yes, right. The problem with their refutation, so the optimal thing would be just to construct MIP star such that the unapproximable character here is already the image of some IRS. Okay, that would be optimal. That would be probably a short proof. Just tinker with MIP star such that you get some character. This character should be induced by an IRS. Then automatically, because all the finitely describable IRSs, okay, they come from actions, so they come from unitaries, right? From from finite dimensional unitaries, they come from finite actions. When I drew this picture for the IRSs, I'm not sure where it is on the board. We had here finitely describable IRSs, right?
Well, my question is about this. I mean, is there a relation between being a finitely describable IRS and being a finitely describable character?
Yeah, the finitely describable, in that sense, the finitely describable IRS is just sent to some finitely describable character.
So how do you find the representation?
It's the action. The finitely describable character, yeah, it's an action, right?
But the other way around.
So take 1 over n trace, you get that, yeah.
Do you think eventually you could show that there are non-sophic groups using this method?
That's a very good question. Like a year ago, maybe, William Slofstra and one of his, I think he was a PhD student back there, Haddock, showed that there is a genuine obstruction in translating. The only thing that makes the MIP star not giving you non-sophic, like why is this not giving you non-sophic groups? That's already could have been done. And that's because of the PCP part of their argument. They're using the PCP theorem somewhere. And you need to linearize, like quantum linearize the PCP theorem, okay? You need some linear constraint system game, which is somehow hard for quantum systems to distinguish between perfect completeness and something with strictly smaller soundness. Okay, so the perfect completeness is the problem usually when in linear systems, but for quantum things, it's not clear why it shouldn't occur. And they have actually shown an obstruction for why, if it appears, you need very deep, like functional analytical reasons to show that. There is no combinatorial simple gadget that will show that. You will need something coming from functional analysis. So it's actually, we are even less optimistic about, our method is even worse in that sense. We don't know of any way of generating, like we know that the thing that we find, so I had this IRSs, right? Finally described IRSs and all IRSs of the free group. We know of an element that lives here, right? We know that it is not supported on calligraphs. Like we can show, our proof method shows that it's not supported on calligraphs at all. So you, at least without doing anything new, you will not get anything. And there are good reasons to believe why, if it's possible, it requires really new ideas. Like it's not, it won't be just a small thing. Yeah, okay.
So what's the question?
Okay, so in the IRSs, in the free group, you have the normal subgroup, the Dirac measures of normal subgroups. Find an element which is here and not here, which is a Dirac measure of some normal subgroup. That's
Sorry, I just meant about, so the existence is, so it just.
That will show, that will show that the group, the free group modulo n is non-sophic. That's what it will show.
Yes. So just to relate two problems, CP and the other side conjecture. You erase now you wrote IRS instead of character. The finite describable characters so are bigger than the finite.
In that sense, you can map the yeah, that's
bigger,
true.
But
That's bigger. Do you have the finite dimensional characters?
Yeah.
They are not actually bigger, right? Because no, they are. Yeah, they potentially they are. You cannot induce always like to an action. That's my question. Like any unitary representation to an action, that's not clear, right? Okay, so they potentially are bigger, yeah.
Potentially are bigger, and all the characters versus all the IRS, there is no relation.
All the characters, again, no. I showed you a way of translating a character to an IRS. If you use this map, any character, if you use this map, you get the picture of the finite dimension characters inside, the finite dimension IRSs inside the finite dimensional characters, inside all IRSs, inside all characters. Yeah, and the problem with MIP star was that they generated something that we don't know to show that it's here and not here. That's essentially the problem with just using their method to refute Aldous Lyons.
But your result does not imply CP because.
Our result also implies.
Internal.
Our result implies CEP just because of that we reprove MIP star is equal to RE, but not because you can automatically.
Yeah.
There is no natural relation between these two problems. It's true that the objects here live inside the object here, but the fact that something cannot be approximated by IRS, it doesn't mean that it's not approximated by characters. And the fact that some character is unapproximable doesn't mean that it's the image of some IRS. That's essentially the tension here.
Are you familiar with, very early on when people were studying this, they showed the free group is not type 1. Familiar with this notion? People were trying to understand the unitary dual. So Harishandra studied the irreducible unitary representation of the semi-simple group. And then you take a lattice inside there, a discrete subgroup inside there. You try to study all the irreducible unitary representations of equivalence. Now, for semi-simple groups, he did that. That's his great work. But if you take the free group, there's this work of Glim, which is it's not type 1, and so everybody ran away from it because you can't decompose into irreducibles. And I wonder if you are not saying something very profound about much more than the complexity of the irreducible unitary representations of a free group, or there are other groups which are not type 1.
But why is it already, why don't you already see it from MIP star, right? Like in their work, they already understood the.
Right, it's just that I've not thought about this Kahn embedding in this way, yeah. I mean, Kahn probably knows the answer to that because he's coming from that generation. But there is this notion of people trying to understand the unitary dual, as you know, with property T. So they try to understand the complete description of the unitary dual, which is given by such positive definite functionals. You can construct a representation backwards from that. Right. And then the lack of the decomposition theory is what says it's a no-no. It seems to me that this is much more profound, but there's something that's probably worth understanding. And I'm just asking you.
Yeah, I didn't think about it. You said that maybe
it's a free group, not type 1.
Yeah.
And it's a description of the unitary dual.
Okay. I don't know. That's a good question. Can we learn something about the unitary dual?
There's something there that they're saying and something quantitative that you're saying that might jive. Yeah. Something that shows a free group is really complicated.
Surprisingly, right?
It's unitary representation, so.
Okay, thank you very much.